Now we look at a more practical scenario in which we move from the static window modeling to dynamic window modeling. The dynamic window modeling is different from static window because 1. Static window was a hypothetical modeling scenario that helped us to understand the effect of the object size, transmission, and propagation delays. But since we are actually interested in seeing how TCP works, we have to move to the dynamic scenario. In this module, first of all, we'll appreciate the congestion control dynamics of TCP because that would give us enough input to make a more realistic translation of TCP behavior in the mathematical model and subsequent simulation. And then we'll start with the classical congestion combat strategy of slow start to model it. The resource I have is Quiroz and Ross. The TCP congestion control dynamics can be best described using this illustration. Here you can see we have transmission rounds or transmission epochs in which the client receives data from the server. And we see here that on the y-axis we have the representation in terms of number of segments. That is, when the TCP starts transmission, it always starts with slow start. It grows exponentially. It reaches a certain threshold, enters into congestion avoidance phase, and grows linearly. When congestion is detected, and if we are talking about TCP Tahoe, the original recommendation of TCP congestion control, the overall TCP system enters into slow start once again because it detects congestion through the timeout interval. But instead, if you look at the working of Renault proposes the detection of congestion through the arrival of 3 duplicate acknowledgements. And that helps it to not fall below to 1 segment, and the congestion window is only halved. As a result, this saves us the trouble of reinitiating the connection from 1 segment. And from there onwards, it grows linearly. Now, these are the congestion dynamics that we expect to model first in mathematical form and then to simulate it. Let's make certain assumptions. The first assumption is that the server starts with congestion window of 1 segment. When the segment is received by the recipient, an acknowledgement is generated. On successful reception of the acknowledgement, the server doubles its congestion window to 2. So 2 segments are sent, 2 acknowledgements would be received. So the congestion window would grow from 2 to 4, 4 to 8, and onwards. This is what we would expect something like. After the first window worth of transmission as 1 segment, when the acknowledgement is successfully received by the server, it is doubled. The third window is again doubled, and the fourth window is yet again doubled. Using basic mathematical manipulation and proper representation of various parameters, the latency has been shown in the book to be twice the round trip time plus the object download time plus a factor p that we see new here times RTT plus S divided by R minus 2 times P minus 1 S divided by R. Here, what we observe is this new factor P introduces a multiplier to the expression of RTT plus S by R and increases the latency considerably. This P is again what we had earlier seen. It is the silence interval. So when we look at these expressions, the first one, that is S divided by R, the segment transmission time, the round trip time, is time from when server starts to send segment until it receives an acknowledgement. 2 to the power k minus 1 into S divided by R is the time it takes to transmit the kth window. The idle time or the stall time after the kth window is represented by the expression shown at the bottom. With this mathematical visualization, as an example, we see here, if we have 15 segments and these segments are sent in the form of 4 windows and the server idles twice, so the latency would be affected like the expression that we have seen earlier here. That is, the value of p is now equal to 2. So the effect of the terms inside the square bracket, that is RTT plus S over R, would be affected with a factor of 2. And likewise, the last expression is represented with the value of 2 to the power p minus 1, which turns out to be 3.